Welcome to SciCuriousID, where we explore the most fascinating phenomena in the universe. Today, we delve into a concept that challenges our everyday understanding of reality. Imagine two particles, perhaps electrons or photons, that are so intimately linked, so deeply connected, that whatever happens to one, the other instantly knows about it and responds accordingly. This connection persists even if they are separated by immense distances, spanning light years across the cosmos. This isn't a concept from a science fiction novel or a fantastical movie. It is a verified phenomenon of the quantum world. This profound and often perplexing connection is known as quantum entanglement, widely considered one of the most mysterious and counterintuitive aspects of our universe.
Behind every question lies discovery. I'm Saluna, and this is SciCurious, where we uncover the science shaping our world.
Indeed, even Albert Einstein, one of the greatest minds in physics, found this concept so unsettling and bizarre that he famously referred to it as spooky action at a distance. He struggled to reconcile its implications with his understanding of the universe. The story of quantum entanglement's acceptance is a fascinating one, rooted in the intellectual debates of the 1930s. It was then that Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, proposed a thought experiment now known as the EPR paradox, specifically designed to challenge the completeness of quantum mechanics. Their central argument was that quantum theory, as it stood, could not be a complete description of reality. They found it unacceptable that two particles, once entangled and then separated, could somehow remain linked, instantly reflecting each other's states without any apparent communication between them. This seemed to imply a hidden, underlying mechanism. Einstein's primary concern was that this instantaneous correlation appeared to violate his own theory of special relativity. According to relativity, no information or influence can travel faster than the speed of light, which is the ultimate cosmic speed limit. The idea of an instant connection across vast distances seemed to contradict this fundamental principle. However, over the course of the next century, a series of increasingly sophisticated experiments would put these theoretical debates to the test. These experiments ultimately proved Einstein both right in his intuition about the spooky nature of the effect, and yet ultimately wrong in his conclusion that it implied faster-than-light communication. The effect is undeniably real, but crucially, it does not allow for information to be sent faster than light. So, how exactly does this spooky action work? The process begins when two particles are created together in a single quantum event. For instance, when an atom emits two photons simultaneously, these photons can become entangled. From that moment, their fates are intertwined. Once entangled, their individual properties, such as their spin or polarization, are no longer independent variables. Instead, they become part of a single, unified quantum state. It's as if they share a common identity, even when physically separated. This shared quantum state means that even if these two particles are separated by millions of kilometers, or even across galaxies, they fundamentally remain part of one single, interconnected system. Their individual identities are subsumed into this larger, shared reality. To illustrate this, consider their spin. If you were to measure the spin of one entangled particle and find it to be up, you would instantly know, without needing to measure the other, that its entangled partner's spin would always be down. This correlation is absolute and instantaneous. However, here's where it gets truly strange. Until that measurement actually takes place, the spin of both particles doesn't have a definite value. Instead, both spins exist in what's called a superposition, a blend of all possible states simultaneously, a cloud of probabilities rather than a fixed reality. The act of measuring one particle forces its superposition to collapse into a definite state. And at that exact instant, its entangled partner, no matter how far away, also collapses into its complementary definite state. This instantaneous correlation is the essence of the spooky action. Crucially, no physical signal or information travels between them to achieve this. Quantum physics suggests that their profound link isn't mediated through conventional space and time. It's a deeper, more fundamental connection that transcends our classical understanding of locality. The prevailing understanding is that the two particles are not separate entities communicating, but rather two manifestations of the same underlying wave function, which itself is spread across space. They are intrinsically linked components of a single quantum entity. Einstein, finding this non-local behavior impossible to accept, suspected that there must be hidden variables, some unknown, underlying properties that predetermined the particles' states from the moment of their creation, thus avoiding any spooky action. However, in the 1960s, physicist John Bell devised a brilliant theoretical framework known as Bell's theorem. This theorem provided a way to experimentally test whether these hidden variables, as Einstein envisioned them, actually existed, or if quantum mechanics' non-local predictions were correct. Over several decades, numerous experiments were conducted by various research groups around the world, rigorously testing Bell's inequalities. The overwhelming results consistently showed that hidden variables, as conceived by Einstein, do not exist. The experimental data perfectly matched the predictions of quantum mechanics, confirming that nature truly does behave in a non-local, entangled manner. Today, quantum entanglement is no longer just a theoretical curiosity or a subject of philosophical debate. It has moved firmly into the realm of practical application. It is now a fundamental resource being harnessed for groundbreaking technological advancements. Scientists are actively using entanglement to build the next generation of powerful quantum computers, which promise to solve problems currently intractable for even the fastest supercomputers. It's also being employed to create quantum cryptography, enabling data encryption with codes that are theoretically unbreakable, and even to achieve quantum teleportation, where quantum information is transferred instantaneously between locations. A landmark achievement occurred in 2017 when Chinese researchers made a significant breakthrough. They successfully entangled particles and maintained that entanglement between a satellite in orbit and a ground station on Earth, separated by an astonishing distance of over 1,200 kilometers. This monumental experiment marked the first successful demonstration of long-distance quantum communication, proving that entanglement could be maintained and utilized over intercontinental scales, paving the way for a truly global quantum network. Building on these successes, physicists in laboratories across the globe are now diligently working towards developing the first functional quantum internet. This revolutionary network will utilize entangled particles to carry information securely across vast distances, creating a communication infrastructure far more secure and powerful than anything we have today. Ultimately, entanglement forces us to fundamentally rethink our understanding of the universe. It strongly suggests that the conventional notions of space and time, which we perceive as distinct and separate, might actually be far more interconnected and fluid than we ever imagined. It implies a profound unity, suggesting that at the most fundamental, deepest level of reality, everything in the cosmos is intrinsically connected, part of a grander, interwoven tapestry. The universe, therefore, isn't merely a collection of isolated particles interacting through forces. Instead, it appears to be constructed from relationships, intricate threads of information and connection that bind even the most distant points together in a vast, cosmic web of quantum entanglement. So, the answer is a resounding yes. Distant objects can indeed be connected in ways that transcend the classical limits of space and time, revealing a universe far more interconnected and mysterious than previously conceived. Quantum entanglement, while not magic in the supernatural sense, certainly represents one of the most astonishing and counterintuitive phenomena in physics, pushing the boundaries of our comprehension and inspiring awe at the universe's intricate workings. If you're curious to explore more mind-bending scientific concepts, and delve deeper into the mysteries of the cosmos, be sure to subscribe and stay curious with SciCuriousID. Join our community of learners as we continue to unravel the secrets of the universe, one fascinating discovery at a time.
There's always more to discover. I'm Selu, and this has been SciCurious. Stay curious, and I'll see you in the next wonder.